Good morning, ladies and gentlemen. It's my pleasure to have a chance to introduce our study about the freezing characteristics of the surface water film over glazed ice by using an ultrasonic puzzle echo technique. My report mainly includes these 5 sections. In recent years, aircraft icing is attracting more and more attention, because in-flight icing is occurred by supercold water droplets accumulated. Local ice sheet is influenced by flight status, aircraft structure shape, and meteorological parameters, and is changed by time. As we all know, safety and economy are the most important factors of civil aviation. However, in-flight icing will do harm to both of them. Surface icing will cause not only the lift-drag ratio to decrease, but also the weight of the aircraft increase, and in serious cases will lead to a plane crash. Besides, it has to consume limited onboard energy by the aircraft icing systems, then bring further economic losses. In order to improve the performance of the aircraft in icing conditions, we should understand the process of aircraft icing more and more clearly. In-flight icing is usually divided into 3 different types, such as glazed ice, rime ice, and mixed ice. Now, we usually classify ice types by different temperatures. For example, the ice formed between 0 to -8 degrees is considered as glazed ice. Rime ice is formed below -20 degrees, and in the intermediate temperature will occur mixed ice. There is no doubt that different types of ice pose different risks to aircraft safety. As shown in the right photo, glazed ice has the severest threat to the flight. What's more, there will exist thin water film over the glazed ice. When the supercold water droplets impact on the aircraft surface, the thin water film is formed. With the water film flow along the surface, it will freeze and release the latent heat at the same time. The shape of horn-like glazed ice is formed, which significantly increases the drag and decreases the lift compared with rime ice. The past researches show that the shape of glazed ice is usually strange due to the complex freezing process of water film. During the process of aircraft icing aggression, a thin transition region is formed between the ice and water layer, while the physical properties of translation layer are in gradient distribution along the thickness direction. However, most of previous studies on icing did not take into account the existence of an ice-water translation layer between ice and water. But this transition layer is objective. It will directly affect the icing process, so it is necessary to study the measurement technology of this transition layer. Till now, ice detectors have been developed over the past 60 years. The commonly used ice detecting methods include visual detecting, vibrating probe detecting, optical detecting, and so on. Most of them are used to find out if there is ice on the surface, but it is difficult to detect the thickness of the ice quantitatively. Since the influence of multi-phase and multi-layer media on aircraft icing process cannot be ignored, and there is a quantitative relationship between the propagation characteristics of sound waves in multi-layer, we select a acoustic method to study the freezing process of supercold water on aircraft surface. As we know, there are 2 kinds of acoustic methods for ice detection. One is ultrasound guided wave, and the other is ultrasonic puzzle echo. Because the in-flight icing phenomenon is ice simulation on leading edge of a wing with large area. As the icing thickness of each region is different, and the ultrasonic guided view cannot quantitatively measure the local ice thickness of this kind of large-scale icing phenomenon, so it is not suitable for aircraft icing thickness measurement. Thus, we select the polycycle method in order to guarantee the accuracy of this measurement. The principle of ultrasonic particle echo detection is shown in pictures. After transmitting and receiving ultrasonic waves through an transducer, we can get the thickness of local ice and thin water films by analyzing the propagation time and sound speed. So it has many advantages, such as superior penetrating power, high sensitivity, greater accuracy, and no damage. The experiment system is established based on ultrasonic pulse echo technique. The system is composed of devices such as ultrasonic emission and reception devices, temperature control unit, water spray device, and so on. To gain the ice sample, the environment temperature is set at -7 degrees. After the ice layer is formed and the ice temperature gets stable, the sprayer is triggered to form the thin water film on the top of the ice layer. As shown, an ice-water transition layer can be clearly observed by an optical microscope. There will be a front of uniform dendritic ice growing into the water film, and researchers describe this transition zone as a multi-phase layer containing water in the ice matrix. In fact, between the water film and glaze ice, the temperature of the transition layer changes linearly, and the thickness of the transition layer is related to temperature gradients and can be calculated. Take the transition layer into consideration. The structure of aircraft icing becomes more complex. Due to this, the ultrasonic signals received from each interface is also changed, as shown in the pictures. Each echo represents different interface of the multi-layer media, and the peak values are related to the material properties. In our study, we use a gradient-based model to describe the transition layer. The transition layer is divided into n sublayers. The index of the sublayer adjacent to the ice layer is 1, and the sublayer index adjacent to the water layer is n, so the material properties in the transition layer can be calculated. Furthermore, we can obtain the reflection material properties in the transition layer. The whole thickness of this transition layer varies in 10 to 20 hundreds micrometers. It means the thickness of each sublayer in the transition layer is identical, and the reflection at each sub-interface can be neglected. First of all, the accuracy of numerical method is validated by comparing experimental and numerical results on a clear glaze ice without water film. The ultrasonic echo waveforms of 1.8 mm thickness ice layer are shown in picture. For example, the simulated transit time of ultrasonic signal in the ice layer is in good agreement with the experimental result, and the relative error is 0.28%. Therefore, ultrasonic piezo echo method for thickness measurement of glaze ice is accurate, and the attenuation of ultrasonic echo signals is negligible. When there exists water film on the surface of ice, the signals changes as shown in the picture. The reflectance of echoes from ice top is calculated as 27.45% based on the results with and without water film. If there is no transition layer between ice and water layer, the acoustic pressure reflectivity of echoes from ice-water interface is 41.67%. The significant deviation illustrates that a transition layer is truly formed between ice and water layer. And the existence of the transition layer will increase the transmission of ultrasonic waves at ice-water interface. The thickness of the transition layer can be determined at 70 micrometers. With the increase of water layer thickness, the absolute value of the peak echo from ice surface firstly decreases and reaches its minimum value. Then the value gradually increases and remains stable. The results suggest that when a certain thickness of water film is attached to the top of the ice layer, the first echo peak of the ice layer is significantly reduced. So, the sensitivity of ice early warning and the accuracy of ice thickness measurements are affected. We can see that it takes 17 seconds for a thin water film with thickness of 180 micrometers to be completely frozen. The minimum thickness of the thin water film that can be measured is found as 42.09 micrometers. The echoes from the ice top are shown on the left for a water film thickness less than 42.09 micrometers. We can find that echoes move towards left and the altitude increase, suggesting the freezing stress of the ice layer is increasing over time. After the transition layer is frozen for 4 seconds, the peak value of echo from the upper surface tends to be stable. The time delay during the freezing will subsequently cause a deviation as about 67 micrometers in ice thickness measurement. It means if the thickness of the stable ice layer is measured as 2 millimeters, the relative error is 3.34% compared to an unstable ice layer. Without considering the influence of external flow field, the initial water film freezing rate is about 10 micrometers per second. This study proposes a multi-layer model to simulate ultrasonic transmission through multiple media in order to reproduce a thin water film that forms on glaze ice and changes in echoes due to freezing. The transition layer between ice and water was simulated and experimentally tested. The key findings are as follows. The ice-water transition layer between ice and air exists objectively and can be characterized by the established model. The thin water film on the surface had a strong influence on echoes from the top of the ice layer. The minimum thickness of thin water film that can be measured is found as 42.09 micrometers. The thickness of the transition layer is determined about 17 micrometers. A delay in echo from top of the ice occurred due to the presence of the water film that caused a relative error of 3.34% in the measurement of the ice. That is all content of my report today. Thanks for listening.